The morning of June 14th, 1944, Aberdeen Proving Ground, Maryland. A German Tiger tank commander's worst nightmare was about to be documented in cold, mechanical precision by his own army's weapons testing division. The Waffenamt-Prüfwesen One report would conclude something American tankers already suspected, but German propaganda refused to acknowledge. The Tiger's vaunted 88mm gun, the weapon that could punch through nearly any Allied armour at 2,000 metres, could not penetrate the upper glacis plate of an M4 Sherman at any range. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Not at 1,500 metres, not at 1,000, not even at point-blank range, assuming the Sherman was angled 30 degrees away from the incoming round. This wasn't American propaganda. This was German military science, tested, verified, and filed away in reports that would remain classified for decades. The engineers who designed the Sherman's armour angle hadn't created a technological marvel. They'd exploited basic physics that German tank designers understood but couldn't replicate on their production lines. The angle wasn't forbidden, it was simply brilliant. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand how American engineers achieved something the Wehrmacht's own testing confirmed, we must return to March 1941, when the United States Ordnance Department began work on what would become the M4 Sherman. The designers faced a fundamental constraint that would define every decision they made: weight. American tanks had to cross the Atlantic Ocean. They had to be loaded onto Liberty ships, transported across submarine-infested waters, and offloaded at ports with limited crane capacity. British and American military planners had established a hard limit. No medium tank could exceed 30 tons if it was going to be deployable in the quantities needed to win the war. German designers faced no such restriction. Their tanks travelled across Europe by rail, allowing the Tiger to weigh 54 tons and the Panther 45. When your tank moves on railroad flat cars from factory to battlefield, weight becomes less critical than firepower and protection. The American solution to this weight problem would be one of the most consequential engineering decisions of World War II. Rather than making the armour thicker, which would add weight exponentially, the Ordnance Department made it sloped. The T6 prototype, completed on September 2, 1941, featured an upper glacis plate, just 50.8mm thick. By comparison, the Tiger's frontal armour measured 100mm, nearly double. Yet when that American armour was angled at 56 degrees from vertical, the effective thickness became 90.8mm, nearly equal to the Tiger's vertical plate, achieved with almost half the actual steel. But effective thickness told only part of the story. The real advantage lay in what metallurgists call the deflection effect. When a projectile strikes sloped armour, it must either penetrate a thickness calculated along the line of sight much greater than the actual plate thickness, or it must change the armour's slope angle through sheer impact force. Most importantly, if the angle is steep enough, the round may simply glance off entirely. The Sherman's designers understood this. What they couldn't have predicted was just how effective their solution would prove against the weapon German tankers trusted above all others: the 88. The 88mm Quai 36 gun mounted on the Tiger One derived from Germany's famous Flak 36 anti-aircraft gun. Its pedigree traced back to Rommel's use of 88mm anti-aircraft guns in an anti-tank role during the North African campaign. Battlefield innovation, born of desperation that proved devastatingly effective. By 1942, the 88 had been adapted for tank warfare. The Tiger's main gun could fire a Panzergranate 39 armour-piercing shell weighing 12.5 kilograms at a muzzle velocity of 930 meters per second. At 2,000 meters, this shell could penetrate 110 millimeters of rolled homogeneous armour. At 1,000 meters, 138 millimeters. At 500 meters, 156 millimeters. These numbers made the 88 perhaps the most feared anti-tank weapon of the war. Allied tankers who encountered Tigers reported watching their armour-piercing rounds bounce harmlessly off German frontal armour, while 88mm shells punched through Sherman turrets from ranges that made return fire impossible. The mythology of the invincible tiger began with these encounters. American tank crews developed a saying, "It takes 5 Shermans to destroy 1 tiger, and you'll lose 4 doing it." The numbers seem to support this. In tank versus tank combat on the Western Front, tigers maintained impressive kill ratios against Allied armor, but those engagements rarely involved shots against a Sherman's upper glacis at optimal angles. Most tank kills came from flank shots, turret penetrations, or hits to the lower hull where vertical armor protected the transmission and differential. The upper glacis, that steeply sloped front plate, was usually bypassed in favor of easier targets. German weapons testers at Waffenamt-Prüfwesen One decided to find out what would happen if the tiger had no choice but to engage a Sherman frontally. The testing methodology was rigorous. German engineers positioned a captured M4 Sherman to simulate combat conditions, angling it 30 degrees away from the tiger's firing position, a realistic battlefield stance for a tank taking cover while presenting the smallest target profile. They loaded standard Panzergranate 39 armor-piercing shells, the same ammunition issued to Tiger battalions in the field. The Tiger's crew fired at the Sherman's upper glacis plate from various ranges. The results contradicted years of frontline mythology. At 2,100 meters, the 88mm round could penetrate the Sherman's differential housing, the lower front hull where the transmission sat. At 1,800 meters, it could penetrate the turret front. These were expected results, confirming the Tiger's superiority in most engagement scenarios. But the upper glacis refused to yield. The German testers fired again. At 1,500 meters, the Sherman's sloped front plate defeated the penetration. At 1,000 meters, still no penetration. They moved closer. At 500 meters, with the Tiger's muzzle velocity at its highest, the armor-piercing round struck the 56-degree glacis and failed to penetrate. The report's conclusion was unambiguous. The Tiger's 88mm gun would not penetrate the upper glacis plate at any range. The physics behind this unexpected result lay in a principle called overmatch, or the thickness-to-diameter ratio. When the diameter of an armor-piercing round significantly exceeds the thickness of the armor plate it strikes, the protection offered by sloping diminishes. The round's mass and diameter allow it to bite into angled armor and normalize its trajectory, reducing the slope's effectiveness. The 88mm round had a diameter of 88 millimeters. Conventional armor theory suggested it should easily overmatch the Sherman's 50.8mm glacis, even when sloped, but the 56-degree angle was so steep that it created a line-of-sight thickness of 90.8 millimeters greater than the projectile's diameter. Combined with the deflection angle, this prevented the round from normalizing its impact trajectory. The German Panther tank, introduced in 1943, would incorporate similar sloping in its design. The Panther's glacis sat at 55 degrees, nearly identical to early Sherman models. German engineers had learned the same lesson American designers had discovered. At high angles, even modest armor thickness could defeat powerful guns. But there was a critical difference in implementation. The Sherman's design from April 1941 had incorporated the 56-degree glacis from its inception. The Panther, rushed into production after the shock of encountering Soviet T-34 tanks with their sloped armor, represented a reactive design. German manufacturing, stressed by Allied bombing and raw material shortages, struggled to produce Panther hulls in the quantities needed. Only 6,000 Panthers were built during the entire war. America built over 50,000 Shermans. The simplified glacis plate on later Sherman models, introduced in late 1943, changed the angle to 47 degrees from vertical. This modification accompanied the transition to larger driver hatches. The earlier Sherman design featured distinctive protruding driver's hoods that compromised the 56-degree angle in 2 specific locations, creating weak points. Ordnance Department testing had revealed that these hood protrusions reduced the effective slope in their immediate area, making them vulnerable to German 75mm and 88mm guns. The solution was straightforward but required retooling production lines, eliminate the protrusions entirely, create larger flat hatches, and accept a slightly reduced angle across the entire glacis. The 47-degree glacis on late-model M4A3 Shermans actually increased protection in the areas previously compromised by drivers' hoods, even though the overall angle was less steep. The uniform slope meant the entire upper plate presented the same ballistic challenge to incoming rounds. Total armor thickness increased to 63.5 mm, providing an effective thickness of 93.1 mm along the line of sight. This uniformly sloped glacis is what German testers evaluated, and this is what the 88mm gun could not penetrate. American tankers in Europe didn't always know about the Waffenamt report. They knew only what they experienced. When Tigers engaged Shermans frontally at long range, rounds that should have penetrated sometimes didn't. Sergeants and lieutenants filed reports describing 88mm impacts on their glacis plates that left gouges, dents, and scorch marks, but didn't penetrate the armor. Some crews believed they'd been hit by rounds that had lost velocity striking obstacles. Others thought German ammunition quality had declined. A few suspected their Shermans had been built with superior American steel. All these explanations contained elements of truth, but the fundamental reason was simpler. The angle worked exactly as the Ordnance Department engineers had calculated it would. The Sherman's side armor told a different story entirely. At 38mm thick and mounted vertically, the hull sides could be penetrated by the Tiger's 88 from well beyond 3,000 meters. The lower hull front, though angled at 56 degrees on early models, was thinner than the upper glacis and protected the vulnerable differential housing exactly the weak point German testing had confirmed at 2,100 meters. This created a tactical reality that American armor commanders learned through brutal experience. Present your glacis, protect your flanks, and never expose your lower hull if you can avoid it. Shermans that maneuvered to keep their upper glacis facing German guns could survive encounters that should have been death sentences. Tanks that exposed their sides, even briefly, burned. The mythology of the Sherman as a death trap or Ronson lighter emerged from these flank shot casualties. American tanks destroyed by flank shots, which accounted for the majority of Sherman losses to German armor, often caught fire when penetrating shells hit ammunition stored in sponsons above the tracks. These fires were spectacular and traumatic for both crews and witnesses, but the flames obscured a statistical reality buried in Ordnance Department reports. Shermans hit on the upper glacis from frontal angles rarely burned because they rarely were penetrated in the first place. The wet stowage system, introduced in March 1944, further reduced fire risk by relocating ammunition to the hull floor and surrounding it with water glycol jackets. Post-wet stowage Shermans penetrated by German fire burned in only 10 to 15% of cases, down from 60 to 80% for dry stowage models. The wet stowage innovation came too late for the Normandy invasion in June 1944, but it arrived in time for the push into Germany. Combined with the improved 47-degree glacis, late-war Shermans represented a significantly more survivable vehicle than the early models that landed in North Africa in 1942. The Waffenamt report's conclusion about glacis invulnerability came with important caveats that German tankers understood implicitly. The 30-degree angle assumption meant the Sherman had maneuvered to present an optimal defensive stance. A Sherman advancing directly toward a Tiger, presenting its glacis at a 0-degree angle, offered a different ballistic problem. The Tiger could still penetrate, though even then, the shot had to strike the glacis rather than glancing off. More critically, the Tiger didn't need to penetrate the glacis when easier targets existed. The turret front at 1,800 meters, the differential housing at 2,100 meters, the sides at any range the gun could reach. German tank doctrine emphasized, shoot at what you can penetrate, not shoot until you penetrate everything. This explains why so many American tankers experienced Tiger superiority despite the glacis. Protection. Tigers engaged at ranges where they could penetrate turrets or lower hulls, maneuvered to get flank shots, and used their superior optics to aim for weak points. The glacis's invulnerability mattered only if the Sherman could force a purely frontal engagement difficult when the Tiger could kill from 2 kilometers, while the Sherman's 75mm gun struggled to penetrate Tigers at any range. But now we must ask a different question. If American engineers had created armor geometry that defeated the 88 at the upper glacis, why didn't they extend this protection to the entire tank? The answer returns us to the fundamental constraint that shaped every Sherman design choice: weight. Every millimeter of armor added to the Sherman's hull represented kilograms that had to be transported across the Atlantic, loaded onto landing craft, and driven across bridges designed for civilian traffic. The engineers at the Ordnance Department faced a brutal calculus: maximize protection where it mattered most, accept vulnerability everywhere else. The upper glacis received the steepest angle because it presented the largest target area to enemy fire during frontal engagements. A tank advancing toward German positions exposed its glacis far more than its turret roof or lower hull. The angle protected the crew compartment. The driver and assistant driver sat directly behind that sloped plate and shielded the vehicle's center of mass. The sides remained vertical and thin because American tank doctrine never intended Shermans to expose their flanks to enemy armor. Tactical manuals emphasized using terrain, advancing in supported groups, and presenting frontal aspects whenever possible. The doctrine assumed correctly in most cases that American numerical superiority would allow positioning multiple Shermans to engage threats from different angles simultaneously. German tank doctrine operated differently. Tigers and Panthers were designed as defensive weapons, holding positions and destroying Allied tanks as they advanced. The German tanks needed thick side armor because they expected Allied tanks to flank them. The Tiger's 80mm side plates could withstand hits from Sherman 75mm guns at moderate ranges, though not from the British 17-pounder or American 76mm guns with tungsten ammunition. This fundamental difference in tactical philosophy meant American and German tanks were solving different problems. The Sherman's glacis angle solved the problem of frontal advance under fire. The Tiger's thick sides solved the problem of defending against encirclement. Neither solution was inherently superior. They reflected different strategic realities. The strategic reality facing America in 1941 demanded quantity over individual superiority. The Ordnance Department projected that defeating Germany would require thousands of tanks deployed across multiple theaters simultaneously: North Africa, Italy, France, and eventually Germany itself. Britain needed tanks. The Soviet Union needed tanks. American armored divisions needed constant replacement vehicles as combat losses accumulated. General Motors, Chrysler, Ford, Fisher Body Division, American Locomotive Company, Baldwin Locomotive Works, Detroit Tank Arsenal, Federal Machine and Welder Company, Lima Locomotive Works, Pacific Car and Foundry Company, and Pressed Steel Car Company all produced Sherman variants. This distributed production meant bombing a single factory wouldn't cripple American tank production. It also meant standardization became critical. The angled glacis had to be producible by both welding and casting. It had to accept the Continental radial engine, the Ford GAA Vate, the General Motors diesel twin, and the Chrysler multibank engine without requiring different hull shapes. The angle had to work with both the original 56-degree small hatch design and the later 47-degree large hatch configuration. This standardization extended to armor plate production. American steel mills produced rolled homogeneous armor to consistent specifications that ensured the 56-degree or 47-degree glacis would provide predictable protection regardless of which factory welded or cast it. Quality control inspectors verified hardness, thickness, and composition, rejecting plates that didn't meet standards. German armor production, by contrast, declined in quality as the war progressed. Allied bombing disrupted supply chains for alloying elements. Forced labor replaced skilled metallurgists. Late-war German tanks sometimes featured armor with inconsistent hardness that cracked under impact rather than deflecting rounds. The Waffenamt report tested a Sherman built when American production quality remained high. Its conclusions might not have held for hastily produced German armor of the same thickness. The M4A3E2 assault tank, nicknamed the Jumbo, demonstrated what American engineers could achieve when weight restrictions relaxed slightly. Developed in early 1944 for the anticipated invasion of France, the Jumbo added 38mm of armor plate, welded directly onto a standard M4 A3 hull. This brought the upper glacis to 101 mm total thickness. Combined with the 47-degree angle, effective thickness reached 150 mm, equal to the Tiger II's glacis. The Jumbo's turret received even more dramatic upgrades: 152 mm on the sides and rear, 180 mm on the mantlet. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. From the front, a Jumbo was nearly immune to the Tiger I's 88mm gun. Only 254 Jumbos were produced. They weighed 42 tons, 12 tons more than a standard Sherman, and their speed dropped from 41 km/h to 35. The additional weight overstressed the suspension, causing frequent mechanical failures. Tank recovery vehicles struggled to tow disabled Jumbos. Bridges rated for 30-ton vehicles couldn't support them. The Jumbo proved that American engineers could create heavily armored assault tanks when needed. It also proved why the standard Sherman couldn't be built that way. An army of Jumbos would have required different ships, different landing craft, different bridges, different recovery equipment, and different logistics chains. The infrastructure to support 50,000 Jumbos didn't exist and couldn't be created in time to affect the war's outcome. So the standard Sherman kept its angled but thin glacis, its vulnerable sides, and its 30-ton weight limit. And that angled glacis kept defeating 88mm rounds that should have penetrated. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Panther's 75mm L70 gun presented a different challenge to Sherman armor. With a longer barrel and higher muzzle velocity than the Tiger's 88, the Panther's gun could penetrate 185mm of armor at 100 meters. The Waffenamt report estimated the Panther would need to close to 100 meters to penetrate a Sherman's glacis when the American tank was angled 30 degrees. 100 meters. That's the length of a football field. At that range, the engagement became desperate and chaotic, both tanks firing simultaneously, crews screaming, engines roaring, visions obscured by muzzle blast and smoke. The Sherman's advantage at 100 meters was rate of fire. The Panther's complex transmission and heavy turret slowed its ability to acquire and engage targets. The Sherman could fire 4 to 5 rounds while a Panther fired 2. But these point-blank engagements rarely happened. Most tank combat occurred at ranges between 500 and 1500 meters, where optics and gun accuracy mattered more than angles and armor. The Panther's superior optics gave German commanders better target identification. The Sherman's gyrostabilizer, a mechanism that kept the gun steady while moving, allowed American tankers to fire accurately on the move. Neither advantage was decisive. The determining factor in most engagements was who saw whom first, who had better positioning, and who had artillery support. The glacis angle mattered when a Sherman had to cross open ground under fire, when retreat wasn't possible, when the only option was to drive directly toward German guns and hope the armor held. Those moments happened more often than tank versus tank duels. Shermans supported infantry assaults, crossed bridges under fire, advanced through towns where Panzerfausts waited in every window. The glacis deflected not just 88mm rounds but 75mm shells from Panzer IVs, 50mm rounds from older German tanks, and critically shaped charge warheads from Panzerfausts and Panzerschrecks. The infantry anti-tank weapons posed an unexpected threat that the angled glacis helped mitigate. A Panzerfaust's hollow charge warhead created a jet of superheated metal that could penetrate 140mm of vertical armor. But when that jet struck sloped armor, its effectiveness decreased dramatically. The shaped charge had to penetrate along the line of sight, and its jet dispersed more rapidly when striking at an angle. American testing in March 1945 confirmed this. Officers from the 1st Armored Group fired Panzerfaust 60s at sandbagged M4s. Shots against the vertical side armor penetrated through the sandbags and into the hull. Shots against the angled front glacis blew away sandbags, but failed to penetrate the armor beneath. The angle worked against hollow charge weapons as effectively as it worked against kinetic penetrators. This made the Sherman more survivable in the close quarters fighting that characterized combat in French villages, German towns, and Italian hill country. A Tiger might dominate open field engagements at 2,000 meters, but in urban combat where ranges dropped to 200 meters and Panzerfausts emerged from cellars and windows, the Sherman's angled glacis provided protection the Tiger's vertical hull sides couldn't match. The Soviet T-34 influenced American thinking about sloped armor more than most histories acknowledge. Soviet tanks captured by Germans in 1941 were studied by American intelligence officers. The T-34's 60-degree glacis, even thinner than the Sherman's at 45mm, proved remarkably effective against German 50mm and short 75mm guns. But American engineers noted the T-34's limitations. The extreme slope created cramped interior space. The driver's visibility suffered. Ammunition storage became difficult. The Sherman's 56-degree initial design represented a compromise between the ballistic ideal of steeper angles and the practical requirements of crew space, ammunition stowage, and production simplicity. Later, when Ordnance Department analysts studied knocked-out Shermans in Europe, they found that glacis penetrations were rare, even in tanks destroyed by German fire. Most kills resulted from turret hits, side shots, or lower hull penetrations. The upper glacis had done its job, it just couldn't protect the entire tank. This created the persistent mythology that would haunt the Sherman's reputation for decades. Crews who survived glacis hits remembered the armor holding. Crews hit in the turret or sides often didn't survive to report. The statistical record showed high Sherman losses over 20,000 destroyed in combat, without distinguishing between losses to glacis failure and losses to hits elsewhere on the vehicle. German tankers contributed to the mythology from the opposite perspective. Tiger and Panther crews reported Sherman inferiority based on their ability to destroy American tanks at long range. They didn't distinguish between glacis shots and easier kills. The narrative of Tiger dominance became self-reinforcing. German crews expected to win, fought confidently, and achieved the results their expectations predicted. But the Waffenamt report told a different story. In controlled testing, without the chaos of combat or the selection bias of survivor accounts, German engineers documented what American designers had calculated. The angle worked. It didn't make the Sherman invincible. It didn't overcome the Tiger's advantages in gun power and frontal armor thickness. It simply made the upper glacis proof against the weapon German tankers trusted most. The Americans who designed that angle in 1941 couldn't have known their calculations would be validated by their enemy's own testing. They knew only that weight restrictions demanded efficiency, and efficiency meant using geometry instead of mass. The 56-degree angle represented the steepest slope compatible with production requirements, crew ergonomics, and mechanical packaging. It also represented something else, evidence that American engineering could compete with German technical sophistication through different means. German tanks emphasized armor thickness, gun power, and individual superiority. American tanks emphasized production volume, mechanical reliability, and geometric efficiency. Neither approach was wrong. They reflected different national capabilities and strategic requirements. The glacis angle's success validated the American approach. 50,000 Shermans with angled glacis plates proved more valuable than 5,000 hypothetical supertanks with twice the armor. Logistics mattered, reliability mattered, the ability to replace losses mattered, and when the angles were right, even modest armor could defeat the mighty 88. The men who crewed Shermans in combat never read the Waffenamt report. They didn't know that German weapons testers had confirmed what some of them suspected. Their glacis could stop an 88. What they knew was simpler and more immediate. Sometimes the armor held, and sometimes it didn't. Sergeant Curtis Coulin of the 2nd Armoured Division never thought about armor angles when he welded steel teeth onto the front of a Stuart tank in July 1944. He was solving a different problem: how to break through the hedgerows of Normandy without exposing his tank's vulnerable underside by climbing over the earthen barriers. His improvised rhino device cut through hedgerows instead of climbing them, keeping the glacis pointed toward German positions. Kulin's invention saved countless Shermans not because it improved the armor, but because it allowed tanks to maintain the tactical positioning where their armor worked best. Glacis forward, hull down, advancing with the upper plate angled toward threats. Within weeks, tank battalions across France were welding scrap metal onto their Shermans, creating the distinctive pronged appearance that would characterize American armor for the rest of the campaign. The crews didn't know they were optimizing for the same geometric principles the Ordnance Department had built into their tanks. They knew only that staying low, moving fast, and keeping the front toward the enemy gave them better chances of survival. The doctrine and the design aligned without the men in between understanding why. By autumn 1944, American armored divisions had developed tactics that maximized the Sherman's strengths while minimizing its weaknesses. Tank destroyers with high-velocity guns engaged German armor at long range. Shermans supported infantry, suppressed anti-tank positions, and exploited breakthroughs. Artillery preparation softened defensive positions before tanks advanced. Air support struck German armor before it could engage American tanks. These combined arms tactics meant Shermans rarely fought the one-on-one duels where German technical superiority mattered most. When a Sherman did encounter a Tiger, 3 more Shermans were usually nearby, maneuvering for flank shots while artillery observers called fire missions. The glacis angle bought time for those tactics to work, deflecting the first shot, maybe the second, creating the seconds needed for support to arrive. The Battle of the Bulge in December 1944 tested these tactics against the largest German armored offensive on the Western Front. German tank formations, including Tiger IIs with even more powerful 88mm L-71 guns, struck through the Ardennes with overwhelming local superiority. American units, often equipped with older dry stowage Shermans, faced the newest German heavy tanks in exactly the kind of engagement German doctrine was designed to win. The results surprised both sides. German advances achieved tactical success, penetrating American lines, capturing territory, destroying hundreds of tanks. But the offensive stalled not because American tanks outfought German armor, but because American logistics, air power, and numerical superiority overwhelmed German capabilities. For every Sherman destroyed, 2 more arrived as replacements. German tanks that ran out of fuel couldn't be replaced. Panthers, broken down by mechanical failure, had no spare parts. The glacis angle didn't win the Battle of the Bulge, but it helped ensure that Shermans hit on the glacis during the chaotic fighting had a chance to retreat, repair, and return to combat. Tanks are only invulnerable until they're not. The question is whether they can survive long enough to be recovered. The angled armor improved those odds. After Germany's surrender in May 1945, American intelligence teams fanned across occupied territory, searching for German technical documents. Among the thousands of reports captured at testing facilities, ordnance depots, and military archives, analysts found the Waffenamt-Prüfwesen One report on Sherman vulnerability. The translators who rendered the German technical prose into English must have paused when they reached the conclusion about the upper glacis. American tankers had reported glacis hits that didn't penetrate. Some commanders had suspected the 88's reputation exceeded its actual capability against angled armor. But here was confirmation from the enemy's own weapons testing division. The design had worked exactly as intended. The report circulated among Ordnance Department engineers who had moved on to designing the Sherman's successor, the M26 Pershing. The Pershing featured a glacis angled at 46 degrees, nearly identical to late-model Shermans, but with 100 millimeters of armor instead of 63.5. Effective thickness reached 140 millimeters, proof against everything except the Tiger II's long 88 at close range. The Pershing's designers had learned the lesson the Sherman taught. Angles multiplied the effectiveness of armor thickness. But they also learned that angles alone couldn't solve every problem. The Pershing weighed 42 tons, the same as the Jumbo, and arrived too late to affect the war in Europe. Only 20 Pershings saw combat before Germany surrendered, and their contribution to victory was negligible compared to the 50,000 Shermans that preceded them. This raised an uncomfortable question for post-war analysts. Would American forces have been better served by more Shermans or fewer Pershings? The mathematics of production capacity suggested that every Pershing built meant 2 or 3 Shermans not built. Given that Sherman losses resulted primarily from flank shots, turret hits, and anti-tank guns rather than glacis failures, would thicker frontal armor on fewer tanks have improved outcomes? The question had no definitive answer. War isn't fought with optimal solutions, it's fought with available resources deployed under urgent timelines. The Sherman's angled glacis represented the best compromise American industry could produce in the quantities required when it was required. The fact that enemy testing validated the design was almost beside the point. The design worked because 50,000 tanks with adequate protection proved more valuable than 5,000 tanks with superior protection. The Waffenamt report contained one additional detail that American analysts noted with interest. German testers had evaluated the Sherman's glacis using standard Panzergranate 39 ammunition, the armor-piercing round issued to Tiger units throughout the war. But Germany had also developed Panzergranate 40, a tungsten-cored subcaliber round with significantly higher penetration. The report noted that Panzergranate 40 supplies were limited and primarily allocated to anti-tank gun units rather than tank formations. The implication was clear. If German forces had possessed unlimited tungsten ammunition for their Tigers, the Sherman's glacis might not have held. But Germany's strategic material shortages meant that the ammunition that could defeat angled armor wasn't available in the quantities needed. This highlighted a broader truth about armored warfare in World War II. Technical performance existed within strategic constraints. The best armor in the world couldn't help if the tank couldn't be fueled. The most powerful gun was useless without ammunition. The steepest angle meant nothing if the factories producing tanks were bombed into rubble. American advantages in industrial capacity, resource access, and strategic bombing ensured that German material shortages worsened as the war progressed. By 1945, German tank production had collapsed, not because engineers couldn't design effective vehicles, but because the infrastructure to build them no longer functioned. The Sherman's angle had to defeat only the ammunition Germany could actually produce and deliver to its tank units, a lower bar than defeating theoretical maximum performance. The Korean War, beginning in June 1950, provided a final test of the Sherman's design against an unexpected opponent. The Soviet T-3485, North Korean tank units equipped with T-34s overwhelmed South Korean and initial American forces, achieving tactical dominance until American M4A3E8 Shermans arrived in theater. The engagements between Shermans and T-34s revealed how much context mattered in armored combat. The T-34 featured a glacis angled at 60 degrees steeper than the Sherman's 47 degrees, with 45 mm of armor. The Sherman's 76mm gun could penetrate this from reasonable combat ranges, while the T-34's 85mm gun could penetrate the Sherman's glacis from similar distances. On paper, the matchup favored neither side decisively. In practice, American crews with better training, better optics, and better tactical coordination achieved favorable exchange ratios. The glacis angle mattered less than crew proficiency and combined arms integration. Both tanks had adequate armor for their roles. The question was which army used them more effectively. By the time the Korean War ended in 1953, the Sherman was obsolescent. The M48 pattern was replacing it in American service, featuring even more sophisticated armor geometry and mechanical design. But Shermans continued serving with Allied nations for decades. Israel used upgraded Shermans as late as the 1973 Yom Kippur War. These late-model Israeli Shermans, designated M51 Super Shermans, retained the original hull with its angled glacis. Israeli engineers added new French guns, improved engines, and better suspension, but they kept the basic armor geometry from 1941. The angle still worked, still deflected rounds, still provided the protection that geometry and physics guaranteed. The engineers who designed that angle in March 1941 couldn't have imagined their work would protect Israeli tank crews 32 years later. They were solving an immediate problem: how to build a medium tank that could cross the Atlantic, survive German guns, and be produced in unprecedented quantities. The 56-degree glacis was one solution among many, chosen for practical reasons and validated by testing. The Waffenamt report proved that sometimes practical solutions derived from constraints produce results that rival or exceed theoretical optimums pursued without constraints. The Sherman couldn't match the Tiger's armor thickness because weight restrictions prevented it. The angled glacis compensated for that limitation so effectively that even the Tiger's main gun couldn't overcome it, at least not when striking the upper plate at realistic combat angles. This wasn't a story about American engineering brilliance triumphing over German technical sophistication. It was a story about different approaches producing different results, both valid within their contexts. German engineers could have built tanks with more steeply angled glacis plates. The Panther proved they understood the principle. But their production methods, tactical doctrine, and strategic situation led them toward different solutions. American engineers could have built heavier tanks with thicker armor. The Jumbo and Pershing proved the capability existed. But their strategic requirements, logistical constraints, and industrial philosophy led them toward the Sherman's compromise of adequate protection through geometric efficiency and overwhelming numbers. The angle wasn't forbidden. It was simply a choice, made early in the war, that proved effective enough to be validated by enemy testing and durable enough to protect tanks across 3 decades of combat. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.